Ni hao, hello everyone, and welcome to the Empower Semiconductor portion of the presentation. Today I'll be speaking about addressing power management challenges of data-intensive applications and what that means. As Mingyu had presented, As Mingyu had presented, I am the Senior Vice President of Sales and Marketing at Empower. And pleased to present today the company overview, technology, and the product performance and implementations options to everyone today. I'd like to thank CASPA certainly for the opportunity and the invitation to present our groundbreaking power management technology today, which will be, I think, first time viewing to many of you on the line today and to this select audience. I look forward to any feedback and questions that you have at the conclusion of the presentation. And I would like to add that you can also go to empowersemi.com to contact us at any time as well. So our mission at Empower Semiconductor is to reduce the energy footprint of the digital economy. And what exactly does that mean? Power management is a fast-growing problem in every end market driven by the increased power complexity of the new digital chips and by the massive increase in data that is moved around the planet each year. IDC predicts that the size of the global data sphere will triple between 2021 and 2025. Each bit requires energy to move and process it, and therefore power management demand increases with the amount and the speed of the data moved. The problem is there's no additional room for power management in these electronic systems. And as you can see in the two examples on the screen, one for mobile phone and the other for a processing card, right? Power is already being squeezed and taking up a huge amount of the availability PCB space or the board space today. And typically it consumes the most important beachfront real estate of the processor. This results in the amount of current that can be provided in a given space. Oh, it keeps switching on me, sorry. Provides in a given space or a power solution's density to increase dramatically over time. This requires an entire new type of power management technology to provide a roadmap to the industry that meets its density requirements, and we started Empower Semiconductor to address this very need. And now a short overview of our company. In order to dramatically reduce the footprint of a complex multi-output power management system, one is inclined to shrink or eliminate all of the discrete components that surround a power management IC. One way to do this is by switching the power supply very fast to reduce the filtering and energy storage requirements. With existing power technology, that will reduce efficiency and increase noise to unacceptable levels. Empower has invented a breakthrough high-frequency technology that eliminates all of the discrete components required by today's power solutions while maintaining high efficiency and low noise. The result is the world's smallest and fastest power management platform that is up to 10 times smaller, 1,000 times faster, and 30% more efficient than existing solutions. By implementing our platform in an advanced CMOS process technology, our platform is fully configurable and programmable digitally on the fly and at high speeds, offering electronic systems unparalleled levels of diagnostics, telemetry, control, and flexibility. We recently closed a $45 million round of Series C1 financing to further accelerate the global expansion of our sales force and operational footprint, as well as to fund development of our next generation Empower IVR and ECAP products. The investment positions Empower well to lead in our target end markets of data center, communications, and mobile. We are located right here, where I'm located in the heart of Silicon Valley, and have a deeply experienced and innovative team with an extraordinary record of on-time performance and successful customer partnerships. We began shipping production product in Q4 of last year, and we're expecting a fast revenue ramp this year and next year as we convert existing power management IC, magnetic inductor, and MLCC sockets into integrated power management solutions. This slide illustrates the incredible improvement in area and component count that our solution enables. On the left is an example of a leading PMIC solution that is in high volume production today. The power management IC, highlighted by the term PMIC in red, consumes only about 10% of the total power solution area. The other 90% of the solution area includes the magnetic inductors, the MLCC capacitors, and resistors that are required by the PMIC for three reasons. One, the slow power management IC switching requires heavy filtering to generate a smooth regulated output voltage. Number two, to provide sufficient energy storage as the bandwidth of the system is too slow to respond to the changing load it powers. And number three, programming of system parameters for the analog functions like loop control, soft start, and supply bias, etc. In total, this system requires 40 components to meet the specification. The design and sourcing is also complex, as all of these components need to be selected, sourced, and tested. All of the individual component variations need to be accounted for in understanding the true performance of the full system over process corners, temperature, and time. On the right is the equivalent in power solution, which integrates all components into a single tiny chip in a fraction of the size. The Empower solution is 10x smaller with 40x less components, yet has more flexibility and configurability. Outside of the incredible breakthrough in size and component count is the performance. With bandwidth orders of magnitude higher than the PMIC solution on the left, the Empower chip can both dramatically lower supply disturbances during transients and increase system efficiency. The reduction in size also has the benefit of making the switching loops very small, which lowers radiated noise versus the PMIC solution on the left. The high switching frequency also allows for simple and effective secondary filtering for very low ripple applications. Empower technology is fully qualified and in volume production. It will have a huge impact on the industry as we know it. Here's a view of our IVR product family available today, the EP70XX family. The product options include a triple, dual, and single output configuration in both package and known good die for use in SoC integration. Output current is available up to 10 amps, and our roadmap is pushing incredible improvements in density as we expand both the voltage and current capability of this technology in order to meet customer demand in our target applications. Look for our new products that come out to market in this year and in next year in the future as well. Now, the physical benefits of the IVR, small size and high bandwidth, enable many performance improvements over existing market solutions. The three panels on the left show a side view of an existing solution example and a couple of different options of our IVR implementations. The red arrows demonstrate the current flow of each solution. The top panel displays how an existing solution, due to its size and thickness, must be placed far away from the load, or the SoC in this case. This results in a long horizontal current flow over to the SoC through a complex PDN network. This path not only carries significant resistance and power loss, depending on the size, the power plane created for the solution, which adds to the overall solution size, but also carries large inductance, which adds to the noise, ripple, and voltage disturbances on the line during transients. This parasitic inductance requires the addition of what is typically several high-frequency bypass capacitors to filter that noise at the SoC. The middle panel illustrates what happens when an Empower IVR with no external components is utilized in a vertical configuration. Due to the 700 micron total thickness of the Empower solution, it can most times be placed right under the SoC where the high frequency bypass capacitors were located. As you will see on the next slide, Empower's fast bandwidth allows the IVR to handle the SoC fast transients without the need for additional local bypass capacitance. The solution also eliminates the long horizontal current flow through the PCB PDN, which will raise system efficiency overall. For SoC suppliers looking to further reduce the power management area and increase the efficiency and performance of the solution further, Panel 3 shows how the Empower IVR and our ECAPs can be sold as known good die and placed inside the SoC package with die thickness down to 100 microns or less. This enables, one, the removal of high current flow through package balls and most of the package PDN, further improving efficiency. Two, even better transient performance and faster DVFS with less parasitic. I keep accidentally hitting the button, losing where I'm at. With less DVFS, with less parasitics between power and the load, and three, through generating multiple voltage rails from one with the Empower IVR in the package, there is a significant reduction in the amount of power rails that must be routed to the SoC, deeply simplifying the PCB layout and the SoC power pinout. Okay, now on to the fun stuff. Actual apples to apples comparison test data. This data is taken from a leading competitor's state-of-the-art PMIC and tested under the exact same conditions with the same equipment as the Empower IVR. Most PMICs specify their transient response with a very slow load, typically on the order of 1 amp per microsecond. This is unrealistically slow and set to the speed in order to deliver reasonable transient response without a mountain of output capacitance and/or having to operate much faster, which will lower their efficiency. In this example, we set the transient to the fastest a competitor PMIC board would allow, an 8 amp step in 230 nanoseconds or 35 amps per microsecond. The scope shot shows the response of the Empower IVR, the blue trace, the competitor PMIC, the green trace, to the load step, which is the pink trace on the bottom. The plot on the left is for an increase in current load transient, and the plot on the right is for an offloading down current transient event. The performance difference is striking and documented in the table. For the upload transient, the competitor PMIC output voltage dips 70 millivolts over 5 microseconds, a nearly 10% excursion for a long period of time, meaning the user may need to set the nominal output voltage up much higher to avoid issues during fast transients, because power consumed on an SoC is proportional to the operating voltage squared, means a 5% increase in nominal voltage results in more than 10% additional power consumed. For the download transient, the situation is even worse, as the load voltages required by today's SoCs don't leave much potential voltage for the DC to DC converter to handle offloading transients. In this case, the PMIC allows the voltage to the SoC to overshoot by 190 millivolts, or nearly 25% for 12 microseconds before it reaches regulation again. Compare this to the Empower solution, which is symmetrical and only allows a 15 millivolt overshoot, and the recovery time is basically instantaneous. Large overshoots can exceed the maximum voltage for a given CMOS process, meaning more output capacitance. Okay. Alongside the IVR product family, we also offer the industry's highest density and widest frequency response capacitors known today. Empower offers both standard and custom product for customers who require low inductance and ESR, or are space constrained with their supply bypass solution. These high performance capacitors are ideal for in-package, under-package, and PCB filtering inductance is typically less than 15 picohenries. And we can thin our integrated capacitors down to less than 50 microns in thickness. These devices are very reliable silicon components that can withstand a wide temperature range and have nearly zero derating over temperature, voltage, and aging, while also providing very accurate cap-to-cap matching. I gotta stop doing that. We can integrate up to dozens of capacitors on a single die to save an immense amount of space. We have a proven custom development process for volume customers to deliver high-performance tested samples in a short period of time in a variety of package and delivery options. All right, in summary, Empower Semiconductor offers novel, high-performance, fully integrated voltage regulators and silicon capacitors. Our products are 3 to 10 times more dense than existing power solutions and offer many ways to improve system efficiency through our speed, density, and simplicity. Our products are first in the industry power supplies on a chip, which can eliminate most of the challenges power designers and SoC developers face in executing the power systems for their solutions, including design trade-offs, components variation, system testing, power routing, and complex BOM and supply management. The high-speed and accurate telemetry and diagnostics for every load given gives system designers critical insights during the product development and validation stage, as well as key reliability and performance data over time during production. That was a quick overview of the company and our products, and I want to thank you for your time and attention. And if you'd like any more information on how Empower can help you meet your power delivery requirements, please reach out to me or to us at empowersemi.com. Guanyan Hao. So thank you very much. I appreciate the time, and certainly wish everyone a happy and prosperous New Year of the Tiger.
Thank you very much, Steve, for your
Thanks,
excellent presentation.
Sure.
Yeah, so we do have questions there from the chat box
Okay.
for your presentation. So the first one is asking about the special cap. So I think this question was asked earlier when you just presented. They were asking if this IVR need a special cap or they can use general one. I think you already answered that using ECAP. But you can still answer that if they could use like a general cap for your IVR or you prefer ECAP.
Sure. Yeah, so I can explain a little bit. So for the IVR itself, there are no capacitance. There is no capacitance needed, no external capacitance. Everything is retained within the packaged product itself. We do use ECAP for our input capacitance and our output capacitance. But there is no external capacitance needed. In fact, it would slow the performance down if it was added. But we have seen cases where customers do have that need. So the ECAP can be used external as well, or as standalone.
Thank you, Steve.
Sure.
Next question is, compared to the PMIC, how much high frequency bypass capacitors can be removed with the IVR? It's almost like a continue your last answer. And the rough percentage number for is good.
Yeah, so we've seen as much as, I mean, it depends on the requirements, the SoC decoupling requirements, but we've eliminated as much as 90% of the bypass capacitance required in some SoC applications. Certainly, I mean, each application is certainly going to be different, but it's a significant benefit because our switching frequency is so much higher. It allows that benefit.
I see. Thank you, Steve. There's a few more questions. Do you have a solution for 500-watt load like NVIDIA GPU? And in case we don't see you said that. So when do you think you will have it?
Yes, that's a great question. It's more of a roadmap question. So the product family that we have today, which you saw, is lower power, more meant for lower power rails, point of load. The technology and the architecture is very scalable. And so we are in the process of developing what has been requested there, which I'll call a high current product that will be able to power GPU and SoC loads as high as 1,000 watts or more. And so that's something that we're working with early adopter partners today. If someone wants more information, they can reach out to me directly, and I'm happy to get in touch for specific details regarding that. But that's a product that's on our roadmap for over the next 4 to 6 quarters, I'll say.
Great, thank you, Steve.
Yeah.
So a few more questions. I think that's should be in your slides.
Okay.
Someone is asking for what is the no good die you're referring to?
Oh yeah, so it's really die solution, right? So the Empower IVR is done in a advanced fine line CMOS process. That's one of the benefits. So it's a very, very tiny die. I'll say it's in one of the most advanced CMOS process technologies used today. So because it's so small, it was originally targeted at integrating the IVR into SoC packages onto substrate applications, right? So therefore, we work with some customers on providing die solutions. So known good just means that it's fully tested, it's compliant, so it's known to be good. Therefore, when it's packaged, it doesn't add further risk to our SoC customers' own product, right?
I see. Yeah. Thank you, Steve, for that. Two more questions, really a lot of questions.
Yeah.
Someone is asking, still inductor inside the IVR. I do see you show the L there though, but I prefer you answer that question. So if you
Yes.
still have an inductor there.
Yeah. There is no, so you need a very small amount of inductance. We have eliminated the need for ferrite-based material inductors because our switching frequency is so high. Essentially, we use air core technology, where the inductors become copper traces, usually either in a substrate or directly below the IVR product itself.
Got it.
Yes.
And yeah, someone is asking, does your silicon capacitor require special process steps?
Special process steps? No, it uses a mainstream CMOS silicon process. No special steps. We have some what we call standard products today, working on expanding, standard product portfolio, but for custom applications, which I guess that's what the question is targeted at, it usually takes about 2 to 3 months from first design confirmation to working silicon. So it's pretty short time.
I see. Yeah, thank you.
Even in today's lead time challenges.
Oh wow, thank you. Yeah. That's very promising. Two more questions we'll take from this session. How is the thermal performance in the IVR package since this integrated? And
Yes.
Since everything is compact inside the package, what is the in-power solution for heat dissipation?
Yes. So the standard solution, or the standard specification that identified the EP70XX family, we call a 10 amp device. That's the specification is 10 amps continuous with no additional thermal management added to the package that it comes in. The peak performance is much higher than that. You can also add heat sinking capability or further thermal pass, but it's very thermally efficient overall, and the die itself inside the package is distributed well thermally. Today we haven't had any thermal management challenges, but we have some customers that want to push it much further, and we work with them on specific thermal management capabilities, heat dissipation capabilities. But the performance overall is pretty good. It's specified to very high temperatures from -40 to 125 C. So the product is very capable.
Thank you. Yeah.
Sure.
I'll take one last question over there. What's the maximum current density of the IVR capacitor could tolerate to sustain the normal operation? It's more about your cap, the ECAP.
Yeah,
I think.
ECAP. I'm trying to understand the context of the question. Current.
Yeah, the question is the maximum current density of the IVR capacitor could tolerate to sustain the normal operation. The more like your ECAP, the operating temperature range, I think. The
operating temperature range or current?
Or I think the way I can just straightly I convert that question to you. The way they ask is what is the maximum current density for the IVR capacitor could tolerate to sustain the normal operation? My understanding, my interpretation to this question is like how your IVR capacitor could sustain, I think, in the normal operation, basically. the max current density. It can serve.
For the IVR or the capacitor?
I believe the capacitor, IVR capacitor.
Oh,
Because
okay.
the current, yeah.
I'll take a note to get back to the
Sure,
person
yeah.
asking that question.
Definitely.
Because I want to make sure I understand. Okay.
Yeah. Sorry. Yeah. You can check that from the chat box.
Okay. I'll
Yeah,
go
I think
look.
that's our last